record. All right, so today we're going to start looking at digital information. And as we go through this unit, we will understand a variety of different ways that computers store information. So first off, I think we all understand that computers don't really store pictures or video or text. The only thing that they understand is numbers. Computers only understand numbers. Specifically, computers only know binary. They don't even understand numbers in the way that we normally think of numbers in like counting up until 10, 11, 12, etc. Computers can only think in binary, and we'll get more into binary later today. And in order to store information on our computers, we need to make sure we're storing information as numbers. So this means that we have all kinds of data that we need to figure out how we're going to store it as a number. And in order to store and manipulate this information, we need to encode information as numbers, like I just said. And we began talking about encoding way back in the beginning of our class. And encoding is just attaching some meaning to some other symbol. So here we're going to be attaching meaning to sequences of digits in order to be able to store information digitally. An example of an information encoding would be a fast food menu. When you go to some fast food restaurant, you know that different orders are going to have a different number associated with them. So you can just tell the person you're asking for food, hey, I would like a number 3. And they know that, hey, you want French fries, because that's what the number 3 means according to their menu. They've encoded French fries into the number 3. Another example is zip codes. Within the US, each different state has some sequence of zip codes assigned to it. So these different codes are going to encode their location as a number. Even we as humans are encoded. So at a very high level, we are humans, and then we can go down to the cell level. Cells are built of proteins, which are constructed out of amino acids, and we know how to put the amino acids in the right order to make the proteins by the code in our DNA. So DNA itself is code for building human beings. So abstraction, we talked about this at the beginning of the year as well. Abstraction is the process of making something complicated into something simpler, into making it more manageable. And there are different levels of abstraction as we're going from something more human readable to something that's more computer readable. So let's think about a word. If I have the word hi, I can break that down into individual characters, H and I. Each of those characters has an ASCII value, which we've learned about in the past. We learned all of the characters that we can think of have some number associated with them. We can convert those numbers into binary so that the computer can read them. And then even at a hardware level, we can say that 0, this thing is going to be turned off. With a 1, it's going to be turned on. So we'll have some sequence of things being on or off to remember that binary encoding. And we can represent that on and off in a variety of different visual formats. So when we have information brought into our computers, we can easily manipulate it in a variety of different ways. If I have an image, I can do various image manipulation things. We're going to learn about image manipulation later in this unit. And we can also examine and filter digital information to gain more knowledge. We can search through it, we can sort it, we can do all kinds of different things with this digital information once the computer is able to interact with it in a meaningful way. A benefit of digital information is that it's often much more compact than it would be physically. So I'm not sure how many of you know what punch cards are, but that is the original version of programming. You would have a physical card in which you would punch holes, and you would feed that through a computer, and that would be the code that you're sending to it. So a webcomic artist that I like, his name is Randall Munroe. He drew a visualization of what it might look like if all digital data across the world were to be stored as punch cards. So if this is the city of Boston, which pretty large city, and this is the thickness of the ice sheet from back when there were glaciers over Boston, this is how thick the layer of punch cards would be. It's ridiculous. There's like, we're storing so much information in, you know, if we were in punch cards, it'd be a huge amount of space. Additionally, it's much easier to transfer digital information than it is to transfer physical information, because we can send digital information over radio waves rather than needing to move some physical object. If you have data written down or stored in a punch card or any other variety of physical media, you have to actually physically move that thing in order to transfer your data. With digital information, we can send it over the internet, we can send it over radio waves, and that will transition it much more quickly and easily than physical data. So if I have some number, I need to figure out how to actually turn it into binary, into ones and zeros, so that I can know how the computer is going to store it. So in order to know how computers store information, we need to know how they think about numbers. And this means we need to understand how the number system binary works. And before we talk about binary specifically, let's talk about what a number system is. A number system is going to determine how a number is represented, which numbers are being used, and what each position within a number is going to represent. So decimal, that is the number system that we are familiar with, that we grew up using. We have 10 digits, 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9 are our digits. Binary, which is the number system that computers use, has 2 digits, 0 and 1. Notice that they both start at 0. There are a large number of other number systems, though. For example, the Mayan number system has 20 digits, starting at 0, going up until 19. We have 20 different digits. The ancient Babylonian number system has 60 digits. So we're not limited to only thinking in 10 and 2. There's any number of different number systems that we can work with. So every single number system is going to fundamentally work the same as every other number system. Each one has its own base, which is used to determine the places within a number in that system. So if with decimal, our base is 10, and we have 10 digits, and those are our digits. In binary, that's in base 2. We have 2 digits. Notice that our base and our number of digits are the same as each other. So let's look at a number in decimal. So how do we count in decimal? We start at 0, we go up 1, 2, 3, 4, 5, 6, 7, 8, 9. What happens when I add 1 to 9? What do I get? We get 10. So let's look at how that works. So all numbers kind of secretly have just a whole bunch of zeros in front. Those zeros don't mean anything because they hold no information. But when I increase this by 1, it's going to overflow back to 0, and I'm going to increase the position of the next digit by 1. So it starts at 0, so it's going to move up until it equals 1. So if I add 1 to 9, I get 10. Then I can add 1 to this again, and I'm going to continue adding in the ones place. I add 1, I get to 2, etc., until I get to 19, at which point that position is going to overflow back to 0. We're going to add 1 to our next place, giving us 20. That is okay, Ashley. So we can keep going until we hit 99, at which point we're going to add 1 to this 9. It's going to overflow to 0. Going to add 1 to this 9. It's going to overflow to 0. And we're going to add 1 to the 0 here, giving us 100. So if we all have all learned how to count in decimal. This is how the number system that we're all familiar with. So let's break it down just a little bit. If I have the number 7,825, 7825, we know we have a ones place, we have our twos place, we have our not twos place, we have our tens place, we have our hundreds place, and we have our thousands place. So we have 7,800, 2 times 10, 20, and 5. Each time we move up, we're going to multiply by a factor of 10. Because 1 times 10 is 10, 10 times 10 is 100, 100 times 10 is 1,000. So I can represent this with multiplications of 10. And even that I can represent as an exponent. Any exponent to the 0 power is going to equal 1. Any value to the 1 exponent is going to equal to itself. And then here I have 10 times 10, that's 10 to the second. 10 times 10 times 10, that's 10 to the third. So I can represent this as 10 to an increasingly large number of powers. Notice that here I have my 10. That's the base of my exponent. It's also the base of my number system. So each position within a number in decimal is going to represent 10 to a given power. So we can find out what number this equals by multiplying the number in that spot by the value that it represents. So 7 times 1,000 plus 8 times 100 plus 2 times 10 plus 5 times 1, it's going to give us 7,000 plus 800 plus 20 plus 5, giving us 7825 in base 10. We use that little subscript to determine what base, what number system we're using to display a number. All right, so now that we kind of have a better grasp of how we use numbers in decimal, let's look at binary. In binary, we only have 2 digits, 0 and 1. So when I have my 0, if I add 1, boom, I get to 1. And then if I try to add 1 to this place again, we still have our leading zeros that don't have any data in them. But when I add 1 to this, it's going to overflow back to 0, and we're going to add 1 to our next index, our next value in our number. So we'll get 1, 0. I can add 1 again. I get 1, 1. When I add 1 to the rightmost thing again, I'm going to overflow this 1 to a 0, add 1 in the next spot. That 1 is going to overflow to a 0. I'm going to add 1 to the next spot. And then this 0 is going to increase to a 1. So we get 1, 0, 0. So it's going to operate the exact same way as in base 10. We just have fewer digits to work with. So we're going to increase our places at a slightly quicker rate. Now, let's look at a number in binary. 1, 0, 0, 1, 0, 1, 1, 0. So broken it up into each of the numbers. Our rightmost number is always going to be our ones place. No matter what, that rightmost thing always going to represent how many ones we have. And then each time we move to the left, we're going to multiply by our base. So 1 times 2 is going to give us 2. 2 times 2 is going to give us 4. And we can continue that pattern. Then we have the 8's place, we have the 16's place, the 32's place, the 64's place, and the 128's place. So that's going to give us 2 to the 0, 2 to the 1, 2 to the 2, etc. as we go up and up. Does this make sense so far? Cool. Okay. So just like in base 10, if I want to find out what number this represents, I can multiply each place by the number it represents. So I'm going to multiply 1 by 128. I'm going to add that to 0 times 64 plus 0 times 32 plus 1 times 16 plus 0 times 8 plus 1 times 4 plus 1 times 2 plus 0 times 1. Let's find all the places that we're multiplying by not 0, because anytime we multiply by 0, we're going to get 0, which adds nothing. So we're going to multiply 1 times 128, 16, 4, and 2. And multiplying by 1 really doesn't do a whole lot. We're just going to get 128, 16, 4, and 2. So when we add all of those together, we get 150 in base 10. So our base 2 number, 100,10110, equals 150 in base 10. Does that conversion make sense? Cool. All right, folks, that is our lesson.